now that we've established that fractals are generated from functions with recursive definitions, what does it mean to have a function with a recursive definition in a processing sketch? This is what we're going to look at exclusively in this video. We'll get to some more advanced stuff later, but we're going to start with this very basic idea. So here we have an incredibly simple processing sketch. It's so nice that in this topic we return back to the kind of very roots of ourselves, the very beginnings of working in processing. We have this sketch that when I run it does nothing but draw this nice, beautiful round circle, this Euclidean form here in the center of the screen, right? All we're doing is making the size, we're saying stroke of 0, no fill, drawing ellipse in the center, 300, 300. So one thing we've learned about in programming is, hey, this functionality here, we could put it into a function. And it's silly to do this because, why are we making a whole other function just to draw a circle? But I could put all of this in this function. I could run it, and I have the exact, so I would have the exact same result if I called the function in draw. So there we go. We have that result right up there above my head, probably there. Okay, so now we've got it in a function. Let's do one more thing, and let's add some arguments to the function. We need a location and a diameter, which will determine the size of the circle. And I'm going to pass those arguments into that function. Okay. Pretty good, pretty basic. If you've been following all these videos, you're way further ahead than this kind of stuff in processing. But now, we're going to add a little twist here. Let's say, what if I were to say call the function draw circle inside of this function? I'm going to do it this way. I'm going to say call it again, but with a diameter that is half the size. Now, first of all, this looks like a horrible idea at first. I mean, are you mad? You just wrote the function draw circle, and then you called draw circle inside of it. So when draw circle gets called, it calls draw circle, which then calls draw circle, which then calls draw circle, and like all of our heads explode in like a madness. In fact, this is really a quite excellent thing to do, and tons of algorithms and things that you might see, and sorting algorithms and all sorts of things can work off of this principle of recursion, a function that calls itself. But there is a problem here that we need to solve. If I were to actually run this, we see nothing on the screen. And in fact, we get this wonderful error message, which I hope you find someday in your life. This sketch is attempting too much recursion, right? It like figured it out. It's like, loop, 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 recursion, recursion. So just as when you first learned about a for loop in processing and you figured out that or a while loop that you need to have an exit condition, we need to have an exit condition for this recursion. What should that exit condition be? Let's think about it for a second. Think about it to yourself. A circle, half a circle, half a circle, half a circle. What about when the circle gets too small? So as long as the diameter is greater than, 10 pixels, which is arbitrary n, then you can continue to call yourself. So if we do this, we now have, and I'll just move this over so I'm not blocking it, we now have, look at this, a circle and then another circle, and eventually we stop calling that function over and over again recursively. Now, if we're looking at this, we're like, okay, come on, you went through all of that, and all you have is a bunch of circles? I mean, I could have done that with a for loop and like lickety-split. And this is true. Everything that you could do with recursion, you could also do with a loop. I don't know if everything, they go back and forth, but there are some things that you're going to see that we can do with recursion that doing with just a plain old loop would be incredibly hard. And I give that as a challenge to you. Look at the kind of examples, all the examples in this particular video. When we get to the end of them, try going back and doing them without recursion. I mean, send them to me. I don't know. I'll be really excited. Okay, so let's just say, what if instead of drawing the circle at the same location, I'm going to draw it a little bit to the right. And now we look at this, we can see I have circles going to the right. Now, let's also say, I'm going to draw that circle a little bit to the left. Now, I'm not going to run this yet, because I know I'm taking a very long time to go over this, but I think it's important to think about. Oops, I left all this stuff here. What did we just do? First we said, draw the circle, and then draw one half the size to the right, half the size to the right, half the size to the right, half the size to the right. And then we said, you know what, to the right and to the left. And so you might think to yourself, here is the result. Right? Circles are going to the right and circles are going to the left. But this isn't the result. We're saying this circle should have a circle to the right and the left. And you know what each of those circles should have? A circle to the right and the left. And you know what each of those circles should have? A circle to the right and the left. Right? This is the power of recursion. We are actually being able to duplicate this kind of multi-dimensional branching shape over and over again. It's like the loop went off in this direction and also this direction and also this direction, but when it goes off in that direction, it also goes in this direction and also this direction. It's really magical. So let's go back, right? Let's come back here and say, remember, what did we do? We're going to comment this line out, and we're going to say, here we go, we've got them going to the right. Now let's add them going to the left. And here you can see, and if we zoom in on this shape here, you can see the majesty of this here. We have them, every circle has two circles around. Of course, it stops, this is the sadness we have, it stops when when we're making a circle that's no more than 10 pixels. We could get a little bit further. We could say, you know what, I don't care, a 2-pixel circle is good enough for me. And now we can really zoom in, and you can start to see, but at a certain point, there's only so much space with these pixels, which is really the tragedy here. One thing that you might consider as a very challenging exercise, I'm just zooming through the operating system's zoom, but what if you built a sketch where you actually could zoom into it? And as you're behind the scenes, you're kind of drawing more and more parts of the fractal depending on what zoom level you're at. That would be a great project. I mean, it's been done a zillion times. Google Mandelbrot set zooming trippy video with colors and cool music. You'll find a ton of them for you to stay up at night and watch with, I don't know, colored glasses and something. But anyway, this is now something we've achieved in processing. And we should also note, that we could keep going with this. What if I wanted to put one above? Right? It should be at the x location, but a little above as well. And we can start to see, I guess above means below when you're adding, right? We can start to see, and what's called, this is so crazy. Look at this. Let's make our window size bigger. This, by the way, somehow just by drawing all of these circles, we get another fractal pattern. That's the Sierpinski Triangle right there. What is the Sierpinski Triangle? The Sierpinski Triangle is a triangle which is broken into 3 triangles, and each of those triangles are broken into 3 triangles, and each of those are broken into 3 triangles, right? I have to watch myself and not keep drawing here, right? We get this. This is a very, very famous fractal pattern, which you could now, as an exercise, also try to create by drawing triangles. How would you create the iterative structure? But it's kind of amazing that we see we've got this just by these circles being overlaid on top of each other. Look at this, it's amazing. Okay, so I forgot how long we've been going, but the next video is kind of important, but I think before we go there, let me just mention one thing. I think somebody correct me, the kind of first known instance of a fractal is about 1883, discovered by the mathematician Cantor, called the Cantor set. Well, the thing that I want to emphasize about these fractals is that they are generated through a recursive function, but they're often come with it a set of production rules. So even though we kind of started with the code, in other scenarios you might start with those production rules. So you can stop the video now because it's probably done enough. But if you're keep interested, then keep listening. So the Cantor set, by the way, has a production rule, which is start with a line. Start with a line. 2 is divide the line into thirds. Right? So that's approximately the line divided into thirds. Erase middle third. So if I get the eraser here and I erase this middle third, this was me applying the production rule to that line. What do we have left over? 2 lines. Let's apply this production rule. Start with a line, apply it to this line, start with a line, apply it to this line. What do we have? That. Let's do that again to 4 lines. The reason why I bring this up, and I wanted to just take a moment, is one of the things about fractals is in this sort of theoretical pretend land where we could do this to infinity, they exhibit these kind of crazy properties. I mean, first of all, we could do this to infinity. We're going to have an infinite number of points just between in this very, very finite space. That doesn't seem really possible. What is, add up the lengths of all of these lines as you do this to infinity. If the first line is 1, the second line is 2/3. What's the next line? Add up the lengths. What happens when you do that to infinity? I encourage you to kind of research and look at a lot of material about the Cantor set and these strange paradoxes. When we look at the Koch curve, it's often referred to as the monster curve because it has an infinite length even though it's in a finite space. So this is really kind of a fascinating thing about fractals, but in our world, we're making stuff with pixels and it's quite finite. But what I wanted to just briefly show you is, you could say to yourself, okay, well, if you understand these production rules, now translate these production rules into a function. And obviously, this is something that this is something that I've done with one of the examples from the book. This, by the way, with the circles is examples 8.1, 8.2, and 8.3, I believe. And once we get to example 8.4, we can see here is the Cantor set. Now, I'm showing each generation as a separate kind of, as a separate line. You can see the first line, then 2 lines, then 4, then 8, then 16, et cetera, et cetera. And you can see how is this done, right? You can take this as an exercise, but you can see the function takes an xy, which is the leftmost point of the line, and a length of the line, and then for every single generation, it draws 2 more lines recursively. So Cantor calls itself twice. So I wanted to just go through these 2 scenarios. There's a kind of essential problem with these 2. I mean, they work, but these shapes are going to be very hard for us to manipulate after the fact. They're just sort of drawn and sitting there. So that's the aspect I want to talk about in the next video. For example, what if you wanted to draw that circular pattern and have all those circles like float away like bubbles? How would you do that? So, and the technique that we're going to look at is using an array list to be our kind of repository of the recursion. And hopefully this kind of gave you the basic idea. Try to generate your own fractal, try to create your own production rules, see if you can create a fractal where you can zoom. There's lots of possibilities there.